let us welcome Dr. Arghya Kusum Das. Okay, he is an assistant professor of computer science at the University of Alaska Fairbanks. He has earned his PhD in computer science with an emphasis in scientific big data analysis from Louisiana State University, USA. Dr. Das's research focuses on the scalable and efficient analysis of scientific big data, for example, genomics, metagenomics, and healthcare data. It includes both development of large-scale software framework and proposing new hardware architectures. For efficient data analysis, his research also focuses on the secure transfer of big data over the internet using blockchain and other decentralized technologies. Dr. Das is currently working towards developing an innovative online platform and curriculums to spread quality of education in the field of big data analytics, AI, high performance computing, and some related technologies. So let us thank Dr. Arghya Kusum Das for giving such an webinar and enriching us with his knowledge. And I thank you all to be present in so such short notice. So thank you, Argo. Over to Argo.
Sure. Thanks, Shoboshachi, for the wonderful introduction. And should I start presenting? I mean, do I have the privilege?
Yeah, you have the privilege. I think you have the.
Okay. Let's see. All right. I can go for the entire screen. I think that's better. Can you see my screen?
Just wait.
Yeah.
It's presenting. Yeah, it's visible.
All right. Can you see the presentation mode or can you see the PowerPoint
Yes,
mode?
it is in the presentation mode.
It is in the presentation. All right, perfect. Okay, so first of all, thank you, Shoboshachi, for inviting me for this talk. And before going to my talk, I would like to thank all of you from Heritage Institute of Technology and everyone else who are joining this presentation and who are going to tolerate me for the next 1 hour. And so, hello everyone. I am Arghya Kusum Das, and everyone here call me Argo. I got my PhD in computer science from Louisiana State University with a focus on big data analytics, and now I am working as an assistant professor of computer science in the University of Alaska Fairbanks. And so here is where I work. It is Alaska's flagship university. Then flagship means it's the best university of Alaska, and its research specialties are pretty well known worldwide, most notably for Arctic biology, Arctic engineering, supercomputing, and all these stuffs, because it is near the Arctic region. It's just 200 miles from the North Pole and from the Arctic Circle. So, and it is the only university in the world where you can access the rocket and satellite launch pad and everything. NASA has a very great research facilities over here, including this launch pad and all these things. And of course, regarding the nature, you can always see like northern lights, glaciers, and many different strange things. And currently it's all night, kind of, because it is the winter, and soon it will be always all day. So you can call good night or good morning based on that. Anyway, so here is my research overview. My research is all about data. So there are 4 different areas of data that I work on. The first one is distributed cyber infrastructure, where I benchmark different cyber infrastructure, collaborate with industry folks, and get their hardware, new innovation in hardware, and benchmark with our proprietary software or something. And then, of course, I work on data science, where I analyze a huge amount of big data in many different fields, especially in bioinformatics and healthcare. there. That's what I am going to discuss today. And also my research focuses on transferring of big data on using blockchain technology, that is the decentralized technology. And finally, I work pretty closely with many faculty members across the world for better data analysis education, for better data education spread over the world. So in today's lecture, I am going to focus on these first two things, that is distributed cyber infrastructure and analyzing scientific big data. And that's why the name of the talk is, the title of the talk is cost-effective acceleration of genomic analysis utilizing modern big data analysis techniques and modern distributed cyber infrastructure. So here is a small agenda. First, I will go over a brief introduction, and then introduction on big data, genomic analysis, and all these things. And after that, in the second part of my presentation, I will discuss about how to analyze scientific big data, a little bit detail of my work. And then in the third part, I will discuss about the distributed infrastructure, which are really required for big data genomic analysis for better performance of the software that we build. And then I will a little bit discuss about my ongoing research initiatives on blockchain and the andragogy and the education of data science. And finally, I will conclude with a call for collaboration from all of you. So here comes the introduction. Big data challenges in genomic analysis. So first of all, let us understand what is genomic analysis. So there are lots of different machines which can actually collect the genomic sample from your blood or from the plant tissues and many different places. So these machines cannot read the entire genome in one go. So what they do basically, they read the genome in a randomly fragmented fashion, sometimes from this part to this part, from that part to that part, like that. So now the point is, so what happened in the last decade, basically these machines who reads the genomic data, they outpace the Moore's law, and which governs the number of chips per die. So what happened? So since they outpaced Moore's law, they started producing a huge amount of data. And here by saying huge, I am talking about at least terabytes scale. And then, so because of that huge amount of data, this huge amount of data is basically putting a lot of pressure on the high performance analysis of that data set, because bundling those small fragments, terabytes of fragments, is not an easy job. It's you need a lot of computation, a lot of memory, a lot of different things. So those are the challenges in the genomic and big data genomic analysis. So now let's have a look at the programming model that we have in hand. The first programming model that I'm going to discuss today is like MapReduce, which is pretty much de facto standard for big data analytics nowadays, where big data is divided into small disjoint subsets, and then user-defined map process, basically batch process it separately, each of the subset, and extract some kind of intermediate information, and then and another user-defined reduce process basically aggregates that intermediate information to give you the output. There are many different MapReduce programming frameworks are available, which are like Hadoop, Spark, lots of different frameworks are available for MapReduce. Then there are some NoSQL database, which basically where basically big data is stored in the format of key and value. It's basically a form of a hash table which enable easy search by key and get the value for the result. These are basically required for faster search or storing lots of data, faster data retrieval, efficient data storage, and for lots of all these things. So here basically there are two different way these things available. One is in memory, like Hazelcast, Redis, when the data is stored in memory, and also there are disk based like HBase and MongoDB. So these are the two different types of model that we need to understand today's presentation a little bit. Now, not only the software side, there are revolution in the hardware side also. If you take the look, if you do the scanning for the last several years, we normally see the trend like processor, storage, memory, network, whatever we see, the cost actually started decreasing and bandwidth is increasing, which is basically changing the performance point and gives us lots of facility to analyze a lot of data. So the main question is how to accelerate, how to leverage all these advancement in the software, programming model, and hardware to analyze the big data genomic analysis. I just discussed the challenges, right? So and also it needs to be in a cost-effective fashion, because if there is no cost involved in it, there is no research actually. Every time all the organization needs to be in budget. So that's what we are going to discuss today. So here in the genomic pipeline, I am going to discuss about one major problem, which is a genomic error correction, which is basically because of the instrumental error for those genome sequencing machines. Several different types of errors are basically introduced in the genome. For example, sometimes these ATGC sequence, some A is substituted to T, or some part of the genome sequence is just deleted, or some extra fragments, erroneous ATGC have been inserted in the genome sequence, something like this. So now, these are the different types. So because of this error, in the downstream analysis, if you can rectify these errors in the downstream analysis, you are going to get lots of different advantages. Your research will be really trustworthy. And so now there are basically two different types of machine, just to give you the idea. One is like known as the Illumina short read sequencing machine, where basically reads the genomes are basically read in very short fragment, like let's say 100 to 250 ATGC per fragments. All right. And then there are something called PacBio type of machine. These are all the name of the companies. Okay, so these PacBio machines basically can read the genome in a longer fragment. Instead of 100 to 200 the base pair only, it can read like 5,000 to 20,000 bases. And here by saying bases, I am saying all about like ATGC type of character through which the genome is represented. Now, this long read is really very useful because it is reading in a long range, right? I mean, so that can provide lots of benefit in the downstream analysis, these longer reads. But the major problem in PacBio is their error rate. It has like 10 to 15% error rates because of its instrumental configuration. Whereas Illumina has only 1 to 2% error rate. So, and here the most type of errors are like indel errors, means some part of ATGC is just somehow inserted wrongly, or some ATGC have been removed wrongly from the genome sequence. So what we need to do is basically we have to leverage the higher accuracy of those Illumina short reads to rectify the PacBio's long read, so that the downstream analysis can get the advantage from these long reads. So the better benefits are like it will be low cost, but however the challenges are like you have to analyze a lot of data. So here are the steps to do the data analysis, to rectify the errors. in indel error basically. So this entire error space, I mean in this entire error correction phase can be mapped as a map problem, I mean sorry, a graph processing problem, can be mapped as a graph processing problem. So this graph basically has a particular name. It is called De Bruijn graph. Now De Bruijn graph in the theoretical sense have a little bit of a different type of notion, but after lots of derivation, after lots of study and all these things, the real meaning is actually basically you have to fragment the genome. Each of the shorter fragments of the genome works as the vertex of the graph. After lots of theoretical derivation, we have found that, well, this is what happens in a De Bruijn graph format. So what we do is how to construct the De Bruijn graph is, first we need to divide each of the reads, like small sequence or large sequence of those ATGC, divide the reads into even smaller substring of length k. And these smaller substrings are basically called kmar because their length is k. K can be any number, 1, 2, 3, 20, 21, something like that. And then each of those small kmars are basically working as a vertex in that graph. And if there are like k-1 prefix and suffix overlap between two kmars, then we assume that there are one edge exists between those two vertex. And so that's how we create the De Bruijn graph in genome sequence. Now there are lots of theoretical derivation how we got all these things. I'm not going into the detail of that, but that's what the notion of De Bruijn graph in here. Now after that, what we did, we have proposed another and widest path algorithm to rectify the error. Now widest path algorithm is basically very common in graph processing, I mean graph theory, which is sometimes called like maximum capacity path problem, where you have to find the widest path. Means basically the problem of finding the path between two designated vertexes or vertices in a weighted graph, maximizing the weight of the minimum edge in that path. So you have to just increase the narrowness of the entire path. That's what the motivation is. So here it is, the indel error correction model. I am not going into the too much detail of the theory here, but just to give you the idea that here actually we have seen the kmar coverage. Coverage means the frequency, how many times each of those small k length substring appeared in the entire genome. So we assume that kmar coverage or this kmar frequency as a IID, as fx, and then we actually applied the theory of minimum probability distribution in order to prove that the probability of the minimum coverage kmar is highest in the erroneous read given many reads sequenced at the same region of the genome. And here is what is the meaning. So if you see the right hand side picture over here, you can easily see that, well, the same region have been sequenced by the machine many times. So no matter what, after proving these things, we can claim that, well, in a path, no matter what, the probability of finding the minimum coverage kmar is maximum in the erroneous path. No matter whether there are several high frequency kmar present or not, but the minimum frequency is finding in the minimum, I mean the erroneous path is maximum. So that's why, and now if we just find the widest path, that erroneous path will automatically remove because it contains the smallest frequency or smallest coverage kmar. So that's the idea. So now in order to develop that theory, we have taken the help of those big data analytic frameworks. Specifically, we have used Hadoop with Hazelcast, and we proposed a software called Parallel, parallel long read error correction with Hadoop. So Hadoop basically is a map reduce framework which is taking care of all the computations, whereas Hazelcast basically takes care of the storage, in memory NoSQL storage. And everything is distributed. They are distributed in a computing cluster over multiple different nodes, and you are for faster computation. So here is the algorithm for De Bruijn graph construction. The thing that I have discussed, the De Bruijn graph. It can be easily an algorithm, map reduce based algorithm can be constructed. That's one was our major contribution. We form a map reduce based algorithm to find to construct that De Bruijn graph, where actually after fragmenting the read in small k-mers, we were taking like first k-mer as predecessor, second k-mer as the current vertex, and the third k-mer as successor. And once we got the information of all the current vertex and its predecessor and successor, in the reduce phase, basically, we are aggregating all the information. So in the map phase, we are getting the vertex and each of the vertex and their predecessor and successor. And then in the reduce phase, we are aggregating all the information to get the vertex, get the entire graph, which is written on the Hadoop distributed file system, again distributed across the node, and it looks something like this. The ATG is a vertex, and TGT and TGC are both like the edges from ATG. So it is a so in this way, it is adjacency list format. We wrote the entire data in the Hadoop distributed file system. The next thing was like indel error detection. In order to do that, we constructed a Hadoop mapper only job. There is no reduce phase in this job. The meaning of map only job is here actually the Hadoop worker basically searches the Hazelcast for the k-mer frequency. And well, the other thing is, at the same time, when we were constructing the De Bruijn graph, when generating all these vertices, all the k-mers, we were taking the count of all the k-mers to calculate the frequency, to calculate their coverage. And we stored it in the Hazelcast in a key value format, like the vertex and their count, vertex, their count, all these different things. Now, then in the second phase, in this indel error detection, we were leveraging that storage. And so what we were used to do, each of the Hadoop mapper was basically searching in the Hazelcast NoSQL distributed across multiple nodes and getting their frequencies. And now the idea was like, if there was like we set up a threshold, and if the k-mer coverage or the frequency of one k-mer is less than that, we were detecting it as an error. If it is higher than that, we were detecting as a true k-mer. So that way we were segregating the error and the highest k-mer. So, and since Hadoop has lots of workers and Hazelcast is also distributed, we were enabling like millions of, not million, let's say thousands of searches per second, and which like millions of searches per 2 to 3 minutes, or per hour or something like that. So and that was very important because the genomic size was very big. And after that, again, we have constructed one Hadoop map only job to develop the widest path algorithm, a distributed version of widest path algorithm, to find out the widest path that I just described. And once we found out the widest path, then the graph is actually rectified. So basically, in this figure, you can understand it. Each of these rectangular boxes are representing the big big frequency k-mers, or greater frequency k-mer means the true regions, and if anything outside those boxes are basically saying that these are the error k-mers. And then from the two different threshold, I mean two different marginal vertexes are taken as the source and the destination, as you can see in here and here. And then we were just finding out the widest path in this entire graph. It is shown in bold line. And once we found out the widest path, then the genome is much better, and it is rectified errors. So that's how we calculate rectified the indel errors. And then substitution error, we have followed another different methods where we have created like Pearson's skew based median based skew coefficient to find the Kmer coverage, and many different theoretical things we have used. I'm not going into that detail now, but here only thing that I would like to say, and that this is a purely statistics based correction. The first problem, the indel error correction, was basically a graph analysis problem, and the substitution error correction with Pearson's skew coefficient, majority voting, you can see these terminologies. These are all purely statistical calculations. The thing is, we have developed the one thing we need to I want to tell, that the framework that I have just proposed with Hadoop and Hazelcast, it is so generalized, the programming models was so generalized that it can handle all these different type of computations, no matter what, whether it is so no matter whether it is a graph analysis or statistical, it was the same distributed framework developed using Hadoop and Hazelcast worked well because of the robustness of the programming model. So that's what our major contribution. And here you can see the data set for evaluation. I am not going into the detail, but I would like to show you that we have analyzed starting from some 50 MB database to data size to 312 gigabytes of human genome data size. So Illumina data set was 312 gigabytes, whereas, the PacBio data set was 312 gigabytes, whereas Illumina data set was 452 gigabytes. So actually we have analyzed 752 gigabytes of data to rectify the human genome. So now you can understand what is the volume of the data I am talking about. And here are several accuracy metrics, and these slides I'm just skipping. Just the main content of these slides are like we tested with many different graph algorithm, starting from Dijkstra's shortest path algorithm, some greedy algorithms and everything. But we have found that our proposed widest path algorithm is giving the best accuracy in terms of aligning the read with some reference genome. And when we compared with existing tools, of course, our tool was more accurate compared to other Lordic and some other tools, which are some existing tools. And now these slides, you can see the scalability basically. So in scalability means we have tested our tool, this Parlake software, on a compute environment compute environment that was allocated by Exceed, LSU, IT, or some LSU was my where I did my PhD. So we used to have a supercomputer. For this thing, I used a supercomputer named Queen Bee. And where this Queen Bee, each node of Queen Bee used to have like 20 Ivy Bridge Intel processor, Intel core. Each of the nodes were equipped with 64 gigabytes of memory, and they have like 250 gigabytes of hard disk drive. And all the nodes were connected using a 56 gigabits per second InfiniBand cable. Now we tested our software with 16 nodes, 32 nodes, 64 nodes, 128 nodes also. And as you can see, we got almost like linear scalability with an appreciable like 55 plus 59 kind of 100 gigabytes of data. So after getting all these things, we tested just to show the capability of our software. We have analyzed these human genome where the entire dataset size is 312 plus 452, that is almost 764 gigabytes. The entire process on 128 nodes with the configuration I just described, it took 28.6 hours. So, well, these are all very computationally intensive. Lots of searches are happening in this huge amount of data. So this type of data time is okay. Why? Because the existing tools, since they are just single node, they cannot distribute properly. They could not even process this data. So that was a big achievement for our research group, actually. And so the idea was, in this phase, basically we got we got like a very nice publications in BMC Genomics, which is one of the top 10 journals in this field, and also there are several conference publication in with lower acceptance rate. So anyway, here actually the main thing that we have achieved, like well, we got significant performance gain using these modern big data analytic programming models. But can we expect more? Can we expect more by utilizing recent advances in hardware infrastructure and kind of like modifying the hardware organization? So that's why, with that viewpoint, with this motivation, we actually started focusing on balanced hardware infrastructure. What kind of hardware infrastructure we should use to expedite, to accelerate our application even more. So that's when we started analyzing what is the meaning of a balanced hardware infrastructure. So this part of the presentation, I'm going to discuss, the heading is a practical model for cost-effective balanced high-performance computing infrastructure. And here, by saying balance, I would like to balance between the CPU, IO, and memory performance and the price, because it is pretty much given. Like, if you add more resources, since our software is scalable, means as you will add computers, more and more computers, you will start getting more and more and more performance benefit. But how many resources will you add? Soon it will just reach the organization's budget, right? Organization's cost consumption wall. At that time, you cannot spend more. So you have to be prudential. You have to be thrifty in your investment. So that's why you need a balanced cyber infrastructure for data-driven science. So we started our analysis with, here actually we have collaborated with many different industry partners as well as academic organizations across the world. For example, IBM, Samsung, several other universities who has like supercomputing services and all these things. So here are some of the example supercomputer where I have worked. Possibly that will be a point of interest for all of you. So here is a supercomputer. It's a blade server. So basically in this small server, this Cray server, there are 8 different nodes, small blade nodes. Each of them has like 32 gigabytes of memory and 2 Intel cores. So this is called a blade server. Then here actually what you can see, this is a traditional supercomputer where I just described the configuration. It was similar to that. The supercomputer name was Queen Bee, and it used to call like SuperMIC. It was in LSU where I did my PhD in Louisiana State University. So here actually each node has, unlike in Queen Bee, it used to have like 64 gigabytes of memory, whereas the SuperMIC used to have possibly 128 gigabytes of memory per node. All the other configurations were kind of same. And then here is something called hyperscale system, where you can see all these small slots. Here actually in this entire chassis, there was like the 21 different computers. So each small slots are basically a different computer here. And each of these computer has like 1 terabytes of SSD, 2 Intel cores, then 32 gigabytes, sorry, 64 gigabytes of memory in this small slot. So this was basically an innovative cluster from Samsung, basically. So we tested on that, and also we have tested our software on world's fastest supercomputer, which is developed by IBM and staying in Oak Ridge National Laboratory. So this is known as Summit. So these are the different type of distributed cyber infrastructure where I have worked for all these things. So basically, in order to come up with the balanced infrastructure, we started our research by finding the issues in a traditional supercomputer or traditional HPC cluster. So why we have found that there are several storage issues, like there are small number of hard disk drive are attached. That's why the IO bandwidth is very low. So big data job becomes very much IO bound. The CPU is just waiting for the reading the data. Then there are several memory issues also, low RAM per core. So how will you store the data? Then there are like network issues also, like because of the performance to price balance, all the supercomputers maintain a blocking. Like if you want to send lots of package, some of them will be dropped, some of them will wait, and it will utilize the next transfer cycle. So those things are basically the issues in traditional supercomputer we analyzed. Then what we did, so then actually we have collaborated with Samsung South Korea to benchmark different types of cluster. So what we did, actually, we went to Samsung research lab. I went there in South Korea, and then basically in their lab we manually changed the configuration all the time. Sometimes we took out some memory slots, sometimes we took out the SSD, replaced with the HDD. So basically we went to their data centers and we changed all the configuration in many different, like let's say in 16 different servers. And this was not only a research work, that was like really tedious work, also lots of manual things. You can imagine, right? In 16 different machine, you are changing the configuration of RAM and memory and all these things. So those things. So anyway, by doing that, we come up with many different type of configuration and we tested it, benchmarked it. So we tested it with our genome assembly. I mean, with our genome construct. I mean, genome assembly benchmark. I just told about the De Bruijn graph construction. With that benchmark software, we benchmarked them. Means we evaluated their performance with a data size of 90 gigabytes. Then so what we have seen, so in all the different configuration, mainly what we have noticed that there is a trade-off between performance and performance to price. Like fewer scaled up server are showing lower performance but very high performance to price, whereas more scaled out server is giving you better performance but not the expected performance to price, basically. So the initial, and also we have observed that after deploying like 4 SSD, we are not being able to we are not getting any more performance benefits. So the question is, what is the optimal point? Where should we stop? Should we use infinite number of SSD to get infinite process? But is it really really possible? So well, the answer was no. We have found that after 500 megabytes per second IO bandwidth, disk controller is actually saturating. So if you want to get more performance, you have to really make the changes in the controller circuit, which is connecting the CPU with the disk. So those type of observations we have done. So the question was, well, those are all the observations. So the main question was how to model these observations to develop an optimal cluster architecture, like, or what is the best way to leverage the SSD. So if we can come up with some kind of a easy to use theoretical model, then that will be used by the hardware vendor to devise the cluster. So that's what our motivation is. So in order to do that, we started delving deeper into the literature, and we saw that, well, computer scientist Amdahl's, possibly you all know Amdahl's law for parallelism or parallel computing, but well, Amdahl has a second law also, where he told that for a balanced architecture, you need to have like 1 bit of IO per second per instruction per second. All right, so this will give you, this type of things will give you a balanced cyber infrastructure where computation is not bottlenecked by either CPU or RAM or disk. So if you can achieve that, then everything is kind of balanced. But he also told that for memory also, there is 1 byte of memory required per instruction, per second. But the major limitation was it is a one size fit all type of model, but big data has lots of different types of application, so it is not enough. So then we saw that great computer scientist, who is the father of data science or data management or this big data analysis, or you can say data-driven science, called Jean Grey. He actually modified Amdahl's law and told that, well, it is said that 1 bit of IO per second per IPS, instruction per second, kept everything same, but on relevant application. But the problem was he did not tell anything about the relevant application. What is relevant application? He realized that, well, there is something related to the application. One size fit all model cannot work, but did not tell anything about the relevant application. And also he changed the memory number, how much memory is required. Amdahl told that 1 byte of memory, he told that, well, 4 bytes of memory, like that. Now the problem is it is just observation, no theoretical background, so it's not very helpful. And also it does not consider the cost component. So what we did, we actually reframed the Amdahl's number, Amdahl's IO and Amdahl's memory number, those balanced terminology, as a different problem. So what we did, we told that Amdahl's IO and Amdahl's memory number is going to give us beta IO and beta mem optimal, are going to give us our the balance between the application and the memory and the hardware infrastructure. So here basically we came up with 2 different things. One is application balance and another is cost balance. Application balance is, and for each of these different things we separated out IO and the memory. So for application balance, what we told, like, well, the required gigabytes per second means the IO bandwidth, 2 required gigahertz, like IO intensive divided by CPU intensive computing. So if it is go high, then it will be IO intensive, and if it goes low, then it will be CPU intensive, like process intensive. The same way application, if it gamma memory, if this number goes high, it is memory intensive. If the number goes low, then it is CPU intensive. So this is what we needed to modify the Amdahl's law like that, and then we have to express it as a function of this gamma IO and this delta IO. So delta is just the same thing, cost per gigabits per second, where cost per gigahertz. We got all the cost and everything from Amazon, Newegg, who are the famous hardware supplier, Dell, Samsung. From their website, we collected all the cost and took the average to come up with this type of cost ratio. So the idea was we have to express this beta IO optimal as a function of this gamma IO and delta IO, application balance and cost balance, both for memory and IO. So in order to do that, what we came up, we just did like the entire processing time we divided into CPU time, IO time, and memory time. For the easy, for our ease of computation, we just ignored any type of overlap, but that does not lose any generalization. So anyway, I am not going into the detail of this theory, but what we did, we just multiplied the execution time with the cost, which is giving us the price to performance ratio. And because performance means 1 divided by execution time, and then replace the resulting cross product with the balance terminologies beta IO and beta mem, and then we partially differentiate this entire thing with respect to beta IO and beta memory, and that gives us the minimum balance when we equate it to 0. So that way, actually, we got like beta IO optimal is basically the square root of the ratio of the application balance between IO and CPU, and the cost balance between disk and the CPU. So this type of number, whereas beta mem is square root of the ratio of application balance between memory and CPU, and the cost balance between memory and the CPU. So this type of formula, small formula, we obtained, we got it. Now this type of small formula can be easily used by the hardware vendors to provide cluster configuration, to make some good quality configuration. So here was the model implication. The only thing that I would like to say today, there are lots of different implications in this figure. The only thing is this model is can predict the future, can work in the future. This is a robust model as the cost will, I mean, because as I told earlier, the hardware cost and hardware performance are changing day by day. Costs are decreasing, bandwidth is increasing, it is changing the entire performance point. So our model will basically hold true with all the changes in the cost also. It will also change itself to predict the actual optimal configuration. So here actually in an example current scenario, we derived the numbers and we got like after collecting the cost from Amazon or Newegg, we got that, well, the beta IO, the IO balance will be 0.17 and the memory balance will be 2.7, something like that. And this series 2 cluster I just described as a hyperscale system few slides back, it was actually similar to that configuration. I mean, here the IO balance is basically 0.17. It's exactly like this. So what happened, and then when we, after configuring this, then we found that, well, that's a very great achievement for us, because every time we were testing with all the different other configuration, all the different other cluster configuration, we always used to get like more than twice benefit in terms of performance to price from compared to any other cluster. Then and not only that, we were getting like almost comparable performance. So the trade-off between the performance and performance of to price that I have discussed, that is gone because of this configuration. And not only that, the better, what was the major finding was, it was, if the data size is bigger, it is going to show us more and more benefit. So that was a great findings for us. For 452 gigabytes, we got like almost 8 times performance to price benefit. So we tested with many different test beds. We just here is like all these things, and we classified all the test bed as traditional high performance computing, data center, and microbrick, which is the hyperscale system. And every time we saw that, well, as I was saying, like series 2, the microbrick or the hyperscale system has beta IO and beta memory. The balanced terminology is almost similar to our performance, what we proposed, the number that we proposed. And this is basically is IO good for IO compute and memory intensive application, whereas the traditional supercomputer with very low beta IO 0.003, only it is good for only compute intensive application, whereas the data center with a little bit of higher beta IO is good for compute and memory intensive application. But this microbrick is good for all different types of application. So we tested it with other benchmark applications also other than our genomic benchmark, and for every time, for all the benchmark, we got better performance with this cluster. So basically this beta IO and beta mem can be used to make more informed choice if your university is trying to acquire some computing cluster or some organizations is buying something. So while investing on HPC infrastructure, you can make some informed decision. And also they are very easy to use and more reasonable alternative for flops, which basically is the current estimation for HPC cluster or supercomputer. And in this phase, we got a very good publication in IEEE Big Data and IEEE Cloud, which are always like less than 20% acceptance rate conference. So that is most about the current talk. So now here is a little bit about my ongoing initiative. In the last 10 minutes, I would like to discuss about that. One is like this genetic risk prediction for complex diseases. For this, I have collaborated with Vanderbilt University Medical Center, which is one of the top medical institute in the world. And with those scientists, I'm actually working for risk prediction. Here, I'm not going into the genetics since it is a technical presentation, but just to give you the idea, here we are exploring the potential of Apache Arrow and Dask distributed framework to see, I mean, how we can improve the performance for the genetic risk score prediction or this PRS score prediction. So that's the technical thing. We are exploring like this a potential of these frameworks. And so that this is kind of what I have done in my genomic side. It is kind of the next step for my work. And I actually work on the blockchain side also, where actually we are developing a platform to facilitate third-party app developers to develop healthcare apps utilizing Ethereum blockchain. Basically, this is an interoperability framework. And so this is in the end product will look like mobile app will look like an Android or iOS like app development platform that provides access to personal healthcare data with user consent and facilitate third-party app developers to develop the healthcare apps. Like it will be like, let's say when you install Instagram in your machine, what it does, it basically asks for your consent that would you like to give permission to access the all the pictures in your machine? You say that yes, and then you can utilize Instagram for many different works. So for editing the image, for publishing the image, all the different things. So this is also like an Instagram type app, which will ask the permission to access the healthcare data instead of image and do all the healthcare related applications instead of image related applications. So it's like that type of platform, and we are focusing on the developing the platform, not the app only. So our motivation is on top of the platform, many different third-party app developer will develop healthcare apps. So here is a broad architecture. I'm not going into the detail of this architecture because of the time constraint, and it is not also the going with the name of the title of this presentation also. But here is a brief architecture what I'm working on. So and the other thing is that, which is very close to my heart, that is I am actually working on online data education and initiative. I have one of my own initiative where I am basically working on developing an online collaborative platform to make data education and the cyber infrastructure that I have just discussed, all these different types of cyber infrastructure, available, affordable, and accessible to anyone, anywhere, anytime. So here actually I'm collaborating with many different companies and institutions across the globe. For example, IBM, Open Power Foundation, Oregon in USA, then TU Delft and PSI in Europe. In India also I have collaborated with Nirma University, Amity University. Recently, this presentation I made before those collaborations, so their name is not here. So anyway, so this is this is very this is a initiative which is very much close to my heart, where I am working very closely in India also, and with many different universities. So here is a screenshot of the web platform that I have developed, and as you can see, there is almost like more than 1,000 students already registered, and they are learning many different types of data science related things. We do face to face, and face to face means synchronous teaching over Zoom, just like this presentation. There are online video materials also free of cost. So lots of different initiatives are there, and here you will not only watch the video or not only attend the lecture, but you will get hands-on on real HPC infrastructure. So that's what my talk is, and here is basically the summary of today's talk. We discussed about the genomic error correction, then also we have, which is basically a data, compute and memory intensive application, and I proposed a framework which I built with Hadoop and Hazelcast for its scalable analysis. And also we have discussed about how to build a cost-effective, balanced cyber infrastructure, which is basically a better alternative to estimate the efficacy of an HPC cluster when it comes to data-driven science. And also I discussed about my ongoing research. And now at this point, I would like to call for a collaboration. You can all visit my institute.herokuapp.com if you want to learn more about data science. We collaborate with Facebook. Recently we launched, recently we have our machine learning, state-of-the-art machine learning type of course, which we teach across India, and not only across India, across the world in many places. So if you want to avail, you can contact me. But at this point, I would like to show a small promo video for Institute and what is the motivation, and that's it. So let me allow to run that video. Okay, so I think here it is. Technology is evolving every day. The jobs are changing at same pace. Learning the right tech skills to be productive is becoming harder and harder. Hiloni got her bachelor's degree in electrical engineering, but landed up in a job at Data Power, a data analysis and IT company in the field of energy and power, where Hiloni needs to develop several new skills. The life was stressful, learning new technologies all by herself and being productive at the same time was really, really hard. It started hampering Hiloni's work-life balance. And Hiloni is not the only one in this story. The entire Indian information technology workforce consists of almost 4.36 million people, among which only 215K students have CS or IT background every year. So that means almost 4.1 million skill gap is still there, which is counting up to 20x gap in required skill and the experts produced in the Indian IT market. So what will Hiloni do now? How can she learn the new skills needed for data analysis and relevant technologies? How can she be productive very quickly? Thanks to Institute, Hiloni registered to the Institute learning platform and developed the skill sets significantly quicker than she thought. I am Arghya Kusum, the developer of the Institute learning platform, and at Institute, our motivation is to make data, computer, and IT education available, accessible, and affordable to anyone, anywhere, anytime. With our proven pedagogical technique, live lectures, and hands-on experiences on cutting-edge hardware infrastructure, we offer the students the best education and prepare them very quickly, in weeks, rather than waiting for months or years. We have strong collaboration with many different academic organizations and industry, which prepare our students with the right skill that the job demands in the current world. After 2 months of launching Institute, we got more than 150 registration already. And after a few sessions in the Indian market and teaching a few students, we got several great review, which prove the credibility of Institute platform. So that's about Institute. Here, data education is one big data problem that we solve. So yeah, that's about Institute, which is a very which is a project which is very close to my heart. And if you want to collaborate with me, you can always join Institute, or you can send me direct email. And well, this video was made when I was an assistant professor in University of Wisconsin Platteville before coming to Alaska. And this was made a little late, and it was only like 150 registration at that time. Now if you go there, you can see like almost 1000 registration is already there. And all right, so that's all, and these are all my related publications. And that's it for today's talk. And yeah, I think I'm almost on time. And so any question now?
Okay, guys, you are free to questions. If you have any doubts or any point which you want to raise, please ask. Or it's although it seems that
I
okay, there's a
think
question.
there are several questions in the chat window I can see. Students of Heritage Institute should be okay.
No, no,
No.
no, no. There's a one question that is asked last. Uh, are big data mostly
Oh,
unstructured? Is it easier to handle structured big data?
yes, of course. I mean, well, a big data, it's not like mostly unstructured. There are plenty of structured data, plenty of unstructured data, plenty of semi-structured data. So no count on that. But it mostly depends on when the industry started collecting the data. If the industry started collecting data from long back when they were using like SQL type of database, their data are kind of structured. And when they started collecting lots of like customer data and like very lately, and their data management platform is not that advanced, their data is like unstructured data. So there are all different types of data: unstructured, structured, and semi-structured. Nothing like mostly unstructured. But yes, it is of course easier to handle structured big data because at least you will have some idea like which column is meaning something or like that. Yes. How do you understand the balance cost of computing versus performance? Is there any standard method? Or well, that's what I just described. So here, if I go to this presentation, if I uh, so here is basically you can get all these things. So this is the formula that we have proposed. This gamma IO and delta IO is going to give you the application balance divided by cost balance. So this is the theoretical formula we have proposed. And just by utilizing this, so let's say you go to the market and then you got like, well, this is my memory. This has a 65, let's say this is 64 gigabytes of memory. So with 64 gigabytes of memory, how much CPU or what type of CPU should I purchase? Just apply this formula to get that balance. And then once you will get that, then make your own configuration, which will be perfectly balanced with memory and CPU. The same way, you go to purchase the SSD, purchase it, and then balance it with the CPU. How much CPU do you need? Or the other way.
So actually, have you gathered those data and then proposed this model, or have you checked by increasing or decreasing the hardwares and then seen the performance? And have you checked it against the error models also?
Oh yes, of course. I mean, everything is was properly checked. Basically, it was scrupulously checked in Samsung South Korea research lab before they adopted it for some of their cluster.
Okay, okay.
Yes, I mean, well, we started with, as I told, we started with some of the benchmark analysis, because before that we didn't have any idea like what are the trade-off. I mean, how the SSD will behave. So first we gather our knowledge that by benchmarking what are the behavior, some empirical things, some in experimental things, and after we got the knowledge, then we started developing the model, and then again tested it back on all the machines. Did I answer properly or any
Yeah,
question?
oh,
Sure.
we got it. I think we got it. We got it. Any further questions, guys? So I think, Orgo, we don't have any further questions. Thank you for your nice and illuminating talk on this data analytics, particularly in how hardware and software can be balanced to get the optimal result. So we are really thankful to you, and we hope that you will come again to this ACM student chapter and give us a talk on your recent topics that you are currently going on, that currently working on. And one more thing to add, congrats for your nice publications.
Oh, thank you.
uh, there
Uh,
is one question, I think, Tanaya Das.
how this field is related to biotechnology, if it is, well, of course, I mean, it is related to biotechnology. So well, I mean, when you are I mean, so well, what we do is we used to collaborate with the biotechnology and the bioinformatics person, and also the biology person in our university. Basically, many department has those genome sequencing machines which are coming from the biotechnology basically. And so from those biotechnology expert we collect those sequence, then we discuss with them closely, and they actually propose that this is the current model that they are current computation they are doing uh, to do the genomic analysis. And then actually we propose all the different types of model uh, to do that. I mean, so here actually we work very closely with both bioinformaticians and biotechnology experts to gather the data and to get the current state of knowledge of the data. And because without that we cannot propose anything. After that we propose our own algorithm, and then again it is tested by the biotechnologist or the bioinformaticians.
Okay, thank you. I hope right now we don't have any questions and all doubts have been cleared. Thank you, Orgo, for coming and giving us lecture on this such topic. So I hope we will meet again. Thank you, Orgo.
Sure, and I would also like to thank you all for attending my lectures and tolerating me for this 1 hour. And I hope you enjoyed it. And once again, if you want to learn more about the data science, more about my research, more about not only my research, many other research, please feel free to join Institute or send me an email. I can help you with all these things. All right, see you.
Okay, thank you,
Thank you.
Orgo.
Thank you. Thanks, Shobhushaji.
Have a nice day. Okay.
You do. Bye.